All right, Calculus 1, Chapter 2, Section 7, Adventurers. I don't know where these things come from. Anyway, I wanted to take a quick look at a set of homework assignments just to make sure that you are prepared to get them started, because starting these problems is often the most challenging part. And in problem number 1, we're considering a parabola. Equation is y equals 8x minus x squared, and we're being asked to find the slope of the tangent line to the parabola at this point. You're going to do exactly what you saw in the video. You're going to be using this equation in conjunction with the limit of the difference quotient. You could put in an a if you want to, or you could just leave it as an x. Go through the process, find the first derivative, and then plug in your x value in order to find the slope of the tangent to the parabola at that point. In order to find an equation of the tangent line from part A, you're going to use point slope form. M is the value that you calculated after taking the derivative and plugging in whatever your x coordinate is. So that's the slope of the tangent line, and then x1, y1 will be these coordinates here. It doesn't look like this assignment discriminates between entering your answer in point slope form versus slope intercept form, but just in case it rejects point slope form, consider converting your equation. Oh, I lied. It says y equals right there. You need to be converting this into slope-intercept form after you get the equation for your line in point-slope form. After you've got your equation, if you want to use a grapher in order to figure out which one of these multiple choice options is correct, that's fine. I think you should be able to do it just by looking at your equations and knowing that your tangent line has whatever slope it has, and that tangent line is passing through whatever point it's passing through. I'm being vague because all these numbers that are printed in red here are going to change algorithmically depending on who's working the problem. Problem number 2 is also asking us to find an equation of a tangent line, which means we need to take the derivative using the limit with the difference quotient, plug in the given x value. In this case it's 25. That'll give us the slope. Then we'll take the slope with x1, y1, which are given to us here as 25, 5, and we'll plug all those in and then convert to slope-intercept form. The difference in this problem from other ones that we've seen is that the use of the difference quotient and evaluation of the limit it's a little bit different. It requires a trick. So I want to make sure that you're aware of what that trick is. We can call it y prime. That's our derivative of this y equals equation. That equals the limit as h goes to 0 of, well, I was going to say f of x plus h, but let's just plug the x plus h in right away. So here's f of x plus h. I'm plugging them into my square root equation. And then it's y2 minus y1. So I'm going to subtract the square root of x, and we're going to divide the whole thing by h. So this is f of x plus h. This is minus f of x. And there's your h in the denominator. You cannot at this moment solve this or evaluate this limit using direct substitution because you'll end up with division by 0. So what are you supposed to do? The answer is we're going to multiply the numerator and denominator by the conjugate. So I'm going to rewrite this. Maybe I'll go vertically. Let's forget that equal sign. Let's come down here. We've got room to work. I'll write this as the limit as h goes to 0. All of this stuff initially is going to be the same. And then I'm going to multiply by 1, which is one of my favorite tricks. Multiplication by 1 is so nice because it changes what your expression looks like without changing its value, because multiplication by 1 does not change the value. And this version of the number 1 looks like this. That's the conjugate of the numerator. The numerator, the only thing that I've changed is the minus into a plus. And then in order for this fraction to be equal to 1, the numerator and denominator must be identical. And here they are. Now in the numerator, I'm going to take this numerator and FOIL it with the second numerator. And then the denominators, we could distribute multiplication by h into the front of either one of these, I almost said absolute values, either one of these square roots, but I'm just going to leave the h on the outside, and you'll see why in a moment. So this is now equal to the limit. Oh, I was going to write a little note over here that we're going to FOIL. Limit as h goes to 0 of, in the numerator, I'm going to FOIL actually, and I'm going to combine like terms, CLT for combine like terms, all in one step. When I multiply my firsts, I'm left with just an x plus h, because it was x plus h times x plus h, which is x plus h square rooted squared. Square root goes away. The o and the I terms are going to cancel out. So far, this bit of multiplication has given me this. The o and the I from the FOILing process are going to cancel out. The L we will retain, and that is negative root x times positive root x, which equals negative x. And then in the denominator, here's my multiple of h, and here's my second denominator. All right, get my CLT on the screen there. Okay, there we go. Now, in the denominator, as I said, I could distribute. I'm not going to. In the numerator, I'm going to combine like terms, which is going to have the x and the minus x cancel out. Now, in this course, because the course that I'm teaching is totally virtual, you're not at any point going to need to show me all of these steps. However, it's possible that some of you are going on to another calculus course, and fingers crossed, you'll have the opportunity to take that one in person. And it might be that that professor requires you to know how to go through the motions of evaluating a determinant using the limit process. So you'll want to know these maneuvers. This is just a nice algebraic trick up here. Now we can evaluate by direct substitution. Almost. We have to do this one other step first and cancel out these h's. That way we don't have division by 0. Your numerator is now a 1. That's a positive 1. Divided by the square root of x plus h plus the square root of x. Now we will evaluate the limit, direct substitution. Put yourself over a little note over here. Phrase it however you want to. We're plugging in h. The limit statement's going to go away, and we end up with 1 over the square root of x plus 0 plus the square root of x, which is equal to 1 over 2 square roots of x. This is the derivative of the square root of x. This is y prime. As you can see here, it's been y prime all along. Now that you have your first derivative, you can take an x coordinate of 25, plug it in, you'll know the slope of your tangent line, then use your slope and your x1 and your y1, plug them into point slope form, for the equation of a line and then convert that into slope-intercept form. This question is interesting. We're looking at it from a graphical perspective, and this is the graph of a position function. A particle starts by moving to the right, and that turns out to be helpful information. Along a horizontal line, the graph of its position function is shown in the figure. S is measured in meters. This is a little bit confusing. This is actually the label on the vertical axis. And along the horizontal axis is time measured in seconds. So what's happening here? We're starting out with a time value of 0, we're progressing to a time value of 1, and what has happened? Our particle has moved 5 meters, S is measured in meters, has moved 5 meters to the right. I know that it's moved to the right because the problem told me that a particle starts by moving to the right. So S, remember, is measuring displacement. So that's how far and in which direction. So we've moved positive 5, so we've gone to the right 5 meters, and then between the time value of 1 and 2, you'll notice that our position hasn't changed. So our distance away from our starting point is neither increasing nor decreasing. Neither increasing nor decreasing. What's the slope of this little line segment right here? 0. Okay? Check out this line segment here from time values 0 to 1. What's the slope of that line segment? It's 5, but maybe more importantly is that it's positive 5. So our distance away from our starting point is increasing. Look at this next line segment. The slope of this one is negative, which means that our distance away from our starting point is decreasing. If I was moving to the right and increasing my distance away from my starting point, how would you then decrease your distance from the starting point? Moving to the left. All right, so I'm going to let you go through and answer the following questions. When is it moving to the right? For which time intervals? For which is it moving to the left? And on which intervals is the particle standing still? You'll notice that all of these multiple choice options have intervals. That's interval notation. Those are time values, and they all are using parentheses. Why would that be? A short answer that's not a super thorough answer is that at these junctures right here, at these corners, our function or our particle is neither increasing nor decreasing in distance away from our starting point. It's almost like both things are happening simultaneously, so we can't make up our mind. At this point where t is equal to 3, is my distance away from my starting point still decreasing? Or is it staying the same? I don't know, it's in a weird transition phase. So we're going to leave it alone, and we'll exclude that actual time value by using a parenthesis or open bracket in our interval notation. Draw a graph of the velocity function. All right, so now let's get a little bit more specific. On this first segment here, from time equals 0 to time equals 1, remember that velocity is a change in position over time, like miles per hour, except here it's meters per second. What is the velocity at any point on that line, or line segment, from time equals 0 to time equals 1? Well, it should be the slope of the tangent line. It's the instantaneous rate of change. Well, all along that upward sloping line, we have the same slope. It has a rise of 5 and a run of 1. So the velocity there would be positive 5 meters per second. So if we changed our graph and the horizontal axis was still time, but our vertical axis was no longer position, if it was velocity, then from 0 to 1, 1, 2, 3, 4, 5, all along there from 0 to 1, you have a velocity of 5. And then, what's the slope of the tangent line from 1 to 2? These are pretty easy because they're all actually lines, so the velocities are consistent. Here you have a consistent velocity. All along here, or I should say all along here, from 2 to 3, you have a consistent velocity. So see if you can use this as a starting point to go through and graph the rest of your velocities with respect to time. So you're going to do that here. Number 4, if a ball is thrown into the air with a velocity of 41 feet per second, its height in feet after t seconds is given by this equation. That's its height. That sounds like position to me. So this is a position function, and yet you're being given a velocity. That's an initial velocity. That would be the velocity when time is equal to 0. Just saying. They want you to then find the velocity when t equals 1. How do you change a position equation into a velocity equation? Take the derivative. How do you find then the velocity when time is equal to, in my case, 1? Take the 1, plug it into the velocity equation. So number 4, use your same limit process as applied to the difference quotient. Find the derivative of that equation and then plug in your time value. Number 5, a rock is thrown upward on the planet Mars with a velocity, that's another initial velocity of, in this case, 14 meters per second at t equals 0. Its height in meters after t seconds is given by h equals, and then there's that equation. That's a position equation. And part A says find the velocity of the rock after 1 second. Instead of using the numerical number 1, they're using the word 1. That's okay, you're still going to plug, in my case, a 1. I would plug a 1 into my velocity equation. Part B, find the velocity when the rock is at a point where t equals a. Instead of plugging in a number, I'm going to plug in the unknown constant value a. So replace all of your t's with a's. Part C, when will the rock hit the surface? Great question. Imagine what's happening here. 0. I guess we're kicking the rock, because if you look at the position equation here and you plug in a t value of 0, your position, your h value would also be 0. So it looks like our rock on Mars, it's being thrown from the ground somehow. Maybe we're standing in a hole and throwing the rock. I don't know. But this equation is definitely for a parabola that's concave down. So it makes quite a bit of sense that this is the kind of flight path that our rock is taking, even if it's being thrown straight up. Point is, it's going up, it's coming back down. Now, the vertical axis is height, and the horizontal axis is t for time for our position equation. And part C says, when will the rock hit the surface? Well, I'm pretty sure that they're asking us about this point right over here, where the rock hits the surface. What's the t value at that point? I don't know yet. That's what they're asking us for. Remember, the question says when? Okay, so they're asking us about t. Do we know what h is when the rock is sitting on the ground? How about 0? Right, so you're going to use that 0 value as an h value. You're going to plug it into your original equation, your original height equation, and solve for t. You're going to get 2 answers. 1 is going to be, oh boy. I just had to scoot over my vertical axis there. One of the t-values that you're going to get is 0. And then you're going to have to figure out what the other one is. That'll tell you when the rock is going to land after its flight from the surface of Mars. With what velocity? Wouldn't it be nice if you already had a velocity equation that was maybe, say, the derivative of the position equation? Take whatever that new time value is, plug it into your velocity equation, and you'll have your answer for part D. Find an equation of the tangent line. What do I need in order to write an equation for a tangent line? Y minus y1 equals m times x minus x1. Well, you're going to need an x-coordinate and a y-coordinate and a slope value. Let's read the rest of the question. Find an equation of the tangent line to the graph of y equals g of x. They're not even telling us what the function is. At the point where x equals 2, and g of 2, which is a y value, equals negative 6, maybe we could use that as a y value. And g prime of 2, that's the slope of the tangent line at a point where x equals 2, that's going to come in handy, is equal to 4. Well, I think that we've got our x1 value and our y1 value and our m value. Now, this is being served to you on a silver platter. That's not always the case. In previous problems, we've had to use the limit in order to find the derivative and then plug in the time value to get the slope. And then sometimes we even had to plug the time value into the original position equation in order to get a y1 value. This one is like you're on holiday, right? They're just bringing it to you poolside. But remember, that's not always the case. That won't always happen. Okay, so an applied problem, the cost of producing X units of a certain commodity is, find the average rate of change. Okay, now this is not an instantaneous rate of change. Now we're talking average rate of change. With respect to X when the production level is changed from 100 to, and then in part 1 or subpart 1, I've got a new X value of 105. Average rate of change is the slope of the line or the secant line between 2 points. Here you're being given the X value of those 2 points. You're going to need the Y values. Those Y values are going to be C values. They're going to be cost values. So you'll have to take these numbers. In my case, I've got 100 and 105. I would have to plug them into my cost equation in order to generate my y1 and y2 values. From there, you can use slope equals y2 minus y1 over x2 minus x1 in order to calculate your slope. And then you're going to redo that process. You're going to keep your x2, y2, and you'll use a new x1, y1. Here's your new x1. You'll plug it into the C equals equation, get your new y1 value, and recalculate a slope. And then, so we've gone from having a difference of, in the problem I'm working, initially I had a difference of 5 between my x values. And then in subpart 2, I only had a difference of 1 between my x values. So my h value went from 5 in the difference quotient to an h value of 1. And now we're going to apply the limit and squeeze that h value down to 0. So for part B, they want the instantaneous rate of change at the point where x equals 100 as a number of units. So you'll need to find your marginal cost equation, which will be C prime, which is also the rate of change of cost. And then you'll plug in an x value of 100 into C prime. And that's it. Finishing with an applied problem. Nice. All right, hopefully that gives you a great start. You've got the tools that you need. Make sure that you're using them in the correct order. And that's pretty much going to be the only challenge in these. in addition to not making any silly arithmetic mistakes. So take it slow, sharp pencil, use lots of paper, spread your work out. You'll do great. See you next time.